In this video, we're going to look at topic 2.3, rates of reaction, which is divided into three kind of main sections. The first thing we'll look at is understanding what we mean by the phrase rate of reaction and how we measure it. The second section, we will look at some practical methods of determining the rate of reaction in an experiment. And finally, in the third section, we'll look at explanations for how we can explain the rate of a reaction depending on a number of different conditions. The first thing we need to know about the rate of reaction is a definition for what we actually mean by rate of reaction. And essentially, the rate of reaction is measuring how quickly you will lose a reactant or make a product over time. So obviously in any reaction, you start with reactants and they turn into products. If you're able to keep track of how quickly the product is made or how quickly the reactants are used up, you've got an idea of how quickly the reaction is going, which is what is meant by rate of reaction. Now, in terms of how you can see or determine the rate of reaction, there's basically two main methods. There's one calculation you can use to very simply turn a time for reaction into a rate of reaction. The other way you can look at it is on a graph and understand the graph's shape to tell you how quick a reaction is going. So firstly, there's a very simple calculation you can use to give you an idea of how quick a reaction is going. And that is just rate equals 1 divided by time, where the time there is the time taken for the reaction to be finished. Time's normally measured in seconds in chemical experiments, so the units for this rate value we've calculated is 1 over seconds, which is seconds to the minus 1. So if you're given a list of times for the time is taken for a reaction to finish, you do 1 divided by those times and that will convert them into rate values. And the bigger the rate value, the quicker the reaction has been going. Another way you can look at a reaction to see how quickly it's going is to plot a graph for that reaction. You've got two basic options. You could plot a graph of how quickly a product is being made, or equally how quickly a reactant is being used up. Because remember, in any reaction, the reactants turn into products. So if we would look at the products being formed, and we're able to track the amount of the product we've got, and then plot it in the graph against time as it's passing throughout the experiment, the graph looks something like this. It would be going upwards, which makes sense because we're making the product. It starts off quite steep and then it levels off as the reaction finishes. If we had a similar graph for keeping track of the reactant, it should go downwards because reactants are used up over the course of a reaction. So we see here the graph's going downwards, it starts off quite steep and then levels off as the reaction finishes. There's just a couple of features of these graphs it'd be useful for you to know. The first thing is the leveling off. So in both these graphs we end up forming a horizontal kind of shape to our curve as the reaction comes towards the finish. Basically, whenever you see a graph like this, keeping track of reactants or products, you can assume that the minute the graph goes horizontal, the reaction has completed, because you're no longer making any more product or you're no longer using up any more reactant. Nothing else is happening. The second thing is about the steepness of the graph. Basically, the steeper the graph is, either in an upward or downward direction, the quicker it's going. Because at the start of this reaction, for example, on the product side, we're making a lot of product in a short amount of time at the start, but then not much product in the same amount of time at the end. It's starting very quick and getting slower. So we could say that the gradient of the graph is proportional to the rate of reaction. The steeper it is, the quicker the reaction is going. Now, one final thing you can do with graphs in this topic is use them to compare two reactions to each other. So let's say I've got another general reaction where I'm making a product and I'm going to be keeping track of how much product I'm making over time. So I'm expecting the same kind of curve I've got in this scenario up above. So again, we start steep and level off and then end up becoming horizontal as the reaction is finished. If I had a quicker reaction than this first one, but had everything else kept the same, so maybe that is the same amounts of the reactant, same amounts of the product, same concentrations. All I'm changing, for example, might be, I don't know, the temperature to speed up the reaction. So how might that look different on this graph? Basically it looks like this. Now there's a couple of things to spot about this red line. The first thing is I mentioned that I haven't changed any of the amounts in this second experiment, so I haven't made any additional product. It's still leveling off at the same amount on the y-axis. I've not made any extra product. But clearly what you can see is that I've got to the finishing point much sooner. It's gone steeper at the start, so we've got a higher gradient here, and also it has leveled off horizontally at a shorter time. These two kind of facts, the steepness and the point at which you become horizontal, show me that this reaction in the red line has taken place much more quickly than the reaction with the blue line. So we'd say the quicker reaction has a steeper line in general and also becomes horizontal sooner. The next section is on practical methods we can use to measure the rate of a reaction. Now, obviously in this section, there's hundreds of potentially different reactions we could use in an experiment to measure the rate of reaction. But to make life a bit easier for you, what your exam board has said is that there's 4 reactions that could come up in this topic as reactions involved in measuring the rate. So we'll look at those just first, then we'll look at the actual method you'd use to measure the rate of those reactions. So the first reaction that could be used is a reaction between magnesium and hydrochloric acid to make the salt magnesium chloride plus hydrogen. The second reaction involves calcium carbonate, often referred to as marble chips because that's normally how it looks like in a container, reacting with hydrochloric acid to make the salt calcium chloride plus water plus carbon dioxide. The third reaction that comes up in this topic is the decomposition, which means breaking apart, of H2O2, which is hydrogen peroxide. So hydrogen peroxide breaks apart into water plus oxygen. Now there's one extra detail you need to know about this reaction. It needs a catalyst for it to work, and that catalyst is specifically called manganese 4 oxide. The last reaction is a little bit different in that you're not actually required to know the equation for it, but it's a reaction between sodium thiosulfate and acid, and what's unusual about this reaction is that it forms a cloudiness or a yellow sulfur precipitate as the reaction takes place. So let's now look at how we can use these reactions in experiments to measure how quickly a reaction is going. There's 3 main methods to look at here. The first method involves measuring a change in mass of a reaction. So for some reactions, they actually get lighter as the reaction proceeds. So you can keep track of that. The lighter it gets more quickly, the quicker reaction is going. If it takes longer to get lighter, the reaction is happening more slowly. So how this will normally work is you'll have your reaction inside a flask on top of a balance, which basically has scales. Now, in terms of what reaction this would kind of work for, you got 2 options basically here. You probably get use of the first reaction or the second reaction. Why we pick these is that they're actually producing gases, so hydrogen and carbon dioxide. So how that will look is that basically it'll fizz. You'll see fizzing within the reaction flask. And if you think about it, gases, even though they're very light, they do have a certain mass to them. So as the reaction fizzes and the gas escapes, what you will actually notice is that your flask will get a little bit lighter as the reaction is going on. So if you put the flask on top of a balance and you look at the reading in the balance, it'll gradually get lighter and lighter as the gas fizzes off. And what you would do is you'd have a stopwatch beside it, and every, for example, 30 seconds, you would take a reading of the mass and keep track of how quickly the mass goes down over time. The only other practical point about this method is you got cotton wool in the mouth of your conical flask. That's basically to stop any splashes coming out. Obviously, you've got liquid in here if you're doing one of these 2 reactions, the acid. And because it's always fizzing very rapidly, some little droplets of acid could maybe escape, and the cotton wool allows the gas to escape but wouldn't allow any droplets of the acid to escape, and that would wreck your results. So the main features to note are that you have the flask on top of a balance. As the reaction fizzes and produces gas, the mass will decrease, which you measure. And the final point is that you put cotton wool on the top of the flask to stop any liquid from escaping. The second method we could use involves measuring the change in the volume of gas produced over time. So again, the more quickly gas is produced, the quicker the reaction, the more slowly the gas is produced, the slower the reaction. So this method works for basically any reaction that produces a gas. So from our examples at the top of the page, we could have any of the first 3. Magnesium makes the hydrogen gas, the calcium carbonate makes carbon dioxide gas, and hydrogen peroxide makes oxygen gas. So any one of these could be tracked using the second method. Basically, your reaction takes place and fizzes and produces gas. The gas is trapped by the seal at the top of the conical flask using a bung, and you've got a delivery tube taking the gas from the conical flask into something called a gas syringe. Basically, a gas syringe is like a big syringe. It's got a plunger in it. So as the gas is produced, the plunger is going to be pushed out, and there's a little scale on the side of the syringe that will tell you the volume of gas that has been produced and that's pushed the syringe out. So again, with a stopwatch, you could take a reading every 30 seconds or so, check how much gas has been produced, and then plot your results in a table. So the gas syringe is pushed out as gas is produced. Now the final method is a little bit different, it's a bit unusual. It involves measuring the formation of a precipitate. A precipitate is basically a solid that's formed when you mix two liquids together or two solutions together. Where we see this is in the forced reaction here. So sodium thiosulfate reacts with acid, and we've said that it produces a sulfur precipitate. How that basically looks is it turns cloudy. You're mixing together two colourless solutions, and eventually the reaction, or the flask, will completely cloud over because you've made this solid. So how you actually turn that into an experiment is reasonably simple. The flask is going to turn cloudy as the reaction proceeds because you're making this precipitate, this solid. So what you would do is you take your flask and actually take a bit of paper with an X drawn underneath it and place the flask on top of that bit of paper. You would then start the stopwatch as soon as the reaction has started, and you would look down from the top of the conical flask, and the very second you think you can no longer see the X because it's turned so cloudy, you would stop the stopwatch. That would actually give you a good idea of how quickly the reaction has taken place. The final section of this topic is how we can explain the rate of reaction using some kind of bullet point explanations. So this would be questions involving you explaining why a particular reaction has got quicker or slower because you've changed a factor such as increase the temperature, increase the surface area, use the catalyst, etc. Now, the way we explain this is using a certain theory known as collision theory. And in a nutshell, it says that any reaction takes place because the particles have collided. So collisions equals reaction. There's one more slight little condition to it, however, which is that for the reaction to take place, you need to have an energetic collision. The collisions need to have enough energy for the reaction to take place. If they don't have enough energy, nothing happens. If they do have enough energy, something does happen. So collision theory states that reactions happen when particles collide, but only particles that collide with enough energy are able to react. So then the question is, well, how much energy do you need? Well, it depends obviously on the reaction, but there is a term we use to describe that kind of barrier to the amount of energy we need. It's known as the activation energy. The activation energy basically means the minimum amount of energy you need for a reaction to take place. And in the language of collision theory, if you have a collision which has enough energy for the reaction to take place, it's a collision that has succeeded, therefore it's known as a successful collision. Successful collisions lead to reactions taking place. So now we see if we can use collision theory to help us explain how changing a number of different factors can lead to reactions speeding up or slowing down. So the first thing we might change is the concentration. So if we increase the concentration of, for example, an acid, we would expect the reaction to speed up. In terms of how we explain it, we got a 3 bullet point explanation. So if you've got a higher concentration in the reaction, you've effectively got more particles of that reactant present in the same volume of liquid. Because there's more particles, there's going to be more collisions, and more collisions means more successful collisions. So there's more successful collisions in a given amount of time, for example per second, and that leads to an increased rate of reaction. The second factor to look at is increasing surface area, which you could achieve by chopping up a solid into smaller and smaller particles. So if you've got a higher surface area, that basically means you've got more particles on the surface of your solid, which means more of them are exposed to the other reactant. That leads to more successful collisions in a given amount of time, and again that leads to an increased rate of reaction. The next factor is increasing the temperature of a reaction. Having a higher temperature means that your particles are moving around more quickly, and that will lead to more collisions and also higher energy collisions. Both of those things mean you're going to have more successful collisions in a given amount of time, and therefore leading to an increased rate of reaction. The final thing to look at is the addition of a catalyst to a reaction. For example, the manganese 4 oxide we add to the hydrogen peroxide reaction. And the first thing just to note is the definition of what a catalyst actually is. So a catalyst speeds up the rate of reaction without being used up itself. And how it achieves that speeding up of the reaction is as follows. So how a catalyst works is that it provides an alternative reaction pathway of lower activation energy. And the effect of that is that you get more successful collisions in a given time because it's now easier for a collision to actually be successful because it doesn't require as much energy anymore. And that again leads to an increase in the rate of the reaction.